Hello trig class, this is our first lecture since moving into an online format, so this is what I'm going to try to do is make these videos for you and get them out to you at the early to mid part of the week. I've kind of made an adjustment this time, so hopefully it'll be a little earlier in weeks to come. But anyway, this is the idea of a polar coordinate, and we'll get into the definition of these in just a second. But this is the visual. This is what we call rectangular coordinates. Why do we call these rectangular coordinates? Because how do I describe this point? I describe it. X is the left to right movement I need to get there. Y is the up and down movement I need to get there. And we typically write the ordered pair X, Y, meaning left to right first, then up and down. But we could also go up and then right to get to that point, and that would create a rectangle in the ways that we describe that point. But no matter where I put this point, notice that the X is how far left and right I go, and the Y is how far up and down I go. And it's hard to see it with the axes on, but that X coordinate is labeled X, and it's like a green dashed line where that's turning. It's not quite as easy to see with the axes on. Let me remove the X axis just for a second so you can see there is a little dashed line there. That's how we get to that point. Okay, so anyway, that's not the only way to describe that point. And so the idea, a polar coordinate, I'm going to turn on this other point. Notice this is d cosine t, d sine t, and d is going to stand for distance. You know, how far away are we from the origin? We are right now 6.4 units. So notice that point, if I move it in to 0, it's no units away from the origin, all the way up to 12 out of the picture, but let's say like right there's 8, right? 8 units away from the origin. So I can describe that purple point right now as the distance away from the origin on the x-axis. But if I keep that distance fixed, like I'm going to try to settle it down here on 7, if I keep that distance fixed, this t, this actually stands for theta, it's like an angle. I can start rotating that point through space, and that little line arc that you see there, that's an angle. Let me move this away. Let's move it over here. And this angle is how far I've rotated this point through through space. Okay, or how far I've rotated it off the x-axis. So I could keep rotating, and let me bring it in a little bit since 6 is as far out as I go. And you can see that I come pretty close to that point. I just missed it barely. Well, since I missed it, what can I do? I can bring it in a little bit. And I still miss it barely because I don't have my angles graduated enough. Let me make my step size, instead of pi over 24, let me make it like pi over 100. Alright, and now when I rotate this, I can rotate a little bit finer tuned, and I can bring that distance in and land basically directly on that point. And the idea is I can, for any point that I have in the plane, if I'm down here in the third quadrant, I can rotate enough to get in the same line from the origin out to that point, like on the same linear path from the origin to the point, and then I just need to extend to the right length to be there. And that idea of rotating a point by an angle is what we refer to as a polar coordinate. Alright, now I'm going to draw in this little dashed line here that connects the origin to that point. So the distance of that blue line is always this 5.9. It's always the same. So it's on like a circular arc. And because of that, it's on a circular arc. That's why trig is kind of at play here, why trig is able to describe it. So the point is, what I'm trying to get you to see here is any point that we have, any rectangular coordinate that we have in the plane, there is an equivalent, and as we'll see later, multiple equivalent what we call polar coordinates for that point. And the way that we label these polar coordinates isn't x and y, meaning how far left and right and how far up and down, because that's rectangular. That's not what we're doing here. What we're doing here is very circular. So the way we label these points is r and theta. Now r in polar coordinates is this, r stands for radius. It's like the radius of this circular path that we're on. And theta is this angle from, again, the positive x-axis that we would rotate to be on the same linear path as this rectangular coordinate. So r and theta in that order, just like x and y is an ordered pair, r and theta is an ordered pair. So you're not going to see, like, 5 pi over 4 in the first position and then a distance in the second position. It's always going to be the distance we are away from the origin first, and then theta, the value second. All right, now I'm going to move back into quadrant 1 just to help us see. I think it's easier to see this in the first quadrant. It works in any quadrant, but in quadrant 1, let's extend this out until where we are right in line with this blue and purple dot. So they're lined up now. Okay, I'm going to move this label up above the point so we don't have all this in the way, and I'm also going to remove that red arc for the time being. And for right now, I'm just going to focus on this triangle there, see, because it's a right triangle again. And I want to talk about how do I convert between these? How do I go from the rectangular coordinate to the polar? How do I go from a polar to the rectangular? Well, honestly, we're looking at it is the Pythagorean theorem. This is r, and we can see with the Pythagorean theorem, x squared plus y squared equals r squared. So that's going to be one of the things that we use to convert between rectangular and polar. All right, so there's the first piece. Now this is, you can think of this also as r equals the square root of this. That's another way if you just want to get r from x and y. Square the x coordinate, square the y coordinate, take the square root, there's r. So you just take the square root of this and you got r isolated. But I write it this way just because it's the Pythagorean theorem, and a lot of people just remember it better if they think of it as the Pythagorean theorem. But we still need r, so we do need to take the square root to get r by itself. Now, how do I get theta? Well, again, where's theta? Theta is this angle right here. So assuming we know x and y, because we're given the point to convert it, then we know the opposite and adjacent side of this angle. So the tangent of what we're looking for is y over x. So therefore, arctangent would give us theta. Now, I encourage you to, instead of using arctangent, to use your unit circle. And again, the reason why that is because we might be in quadrant 2, we might be in quadrant 3, all right, we might be in quadrant 4 with a positive angle. And arctangent, again, just like in the equations chapter, it only gives us first quadrant and fourth quadrant negative angles. So it's not going to give us that. So I strongly encourage you to use the tangent function. Tangent theta equals y over x. Okay, so it's completely up to you if you want to call it arctangent. Theta equals arctangent y over x. But again, if you're comfortable using arctangent from the last chapter, the equations, then you'll know if you want to work with it that way. That's what they'll call it in the book if you look on View an Example. But I'll just like to say tangent and then just use my unit circle. All right, let's do one of these. Let's practice it and see if we can understand how to do this. Okay, my point right here. This point is -4, -4. So this is a quadrant 3 point. -4, -4. I want to come up with a polar coordinate that would put me at the exact same position. All right, well, let's do the Pythagorean theorem. X squared, all right, that's negative 4 squared, so that's 16, plus y squared. Alright, that's negative 4 squared, also 16. So 16 plus 16 is 32, so r squared is 32, so r is the square root of 32. Alright, and remember the square root of 32, that is the same thing as the square root of 16 times 2. Alright, and because that's a product underneath the radical, I can write it as the square root of 16 times the square root of 2. Notice we keep getting that same number, 5.66 roughly. And then the square root of 16 is 4. So there's r. r is 4, square root of 2. Now watch what I'm going to do here. Desmos has a built-in polar mode. So if I type in r equals in front of that 4 square root of 2, and by the way, I can take away that times dot, it will put a circle on here with the radius 4 square root of 2. And notice it goes right through the center of that point. Okay? And notice this also, it has this polar mode. It's like how much of the circle do you want to graph, and by default it gives you all 0 to 2 pi. So if I wanted to make it only half of a circle, I could write 0 to pi. 3 pi over 2. It only does 3/4 of a circle. 3 pi over 4. Alright. 3 pi over, 6, which would be pi over 2. Okay, so just showing you that it can cut that off, but by default, again, it goes to 2 pi if you don't say anything. But anyway, r equals is the default notation for polar. R equals 4 square root of 2. That just means a circle with a radius 4 square root of 2. That's what it means to Desmos. Okay, now what does my angle need to be? Well, x and y are equal, right? X equals y. So y divided by x would be negative 4 divided by negative 4, which is 1. So the tangent is 1. Where's tangent 1? Well, it's 1 at 45 degrees in quadrant 1, right? And it's also 1 if we add pi radians to that and come down here in quadrant 2. Okay? Or sorry, quadrant 3. I can't get quite on it. It's skipping over. But anyway, the value that we're getting there would be r would be 4 square root of 2, and theta would be that it's 1 pi over 4, 3 pi over 4, 5 pi over 4. All right. Now what I want to write to get Desmos to do this is, I'm going to take away my circle, is let me take this away too. Like this. D was my distance, so that's r. So it's just like r cosine theta. So r was 4 square root of 2 cosine of what was theta? Theta was 5 pi over 4, comma, and then this is r. Right, I got it labeled as d, but it's r for this notation. R sine theta. R is 4 square root of 2 times the sine of 5 pi over 4. Oops. There. Alright. And I'm going to label this polar, so you can see that that's the point it's labeling. It's labeling the one that we just plotted there. Oops. Didn't mean to close that off. Alright, and I'm going to pause this and take away. Alright, and there is how we get our polar coordinate from x and y. Alright, how do we do it? We get r with the Pythagorean theorem. Alright, that's the 4 square root of 2 here. And then how do we get theta? I use tangent. Alright, the tangent of theta was equal to 1 here. Y divided by x. I divided the y coordinate by the x coordinate. Set tangent equal to that, and then just looked on my unit circle. Alright, and quadrant 3, tangent's equal to 1 at 225 degrees or pi over 4 radians, and that's how I did it. Okay, so it's not bad switching from the rectangular to polar. Now, switching from polar to rectangular, how would I go from something that looks like this, 4 square root of 2 comma 5 pi over 4, how would I go from that to knowing that that is this? Well, if we remember that in this triangle, the sine of the angle is opposite y over hypotenuse r, and cosine is the adjacent over the hypotenuse. Right? If we remember that, then we get the way to convert back. How do I get x? Well, just solve this for x. Multiply both sides by r, and you get x equals r cosine theta. Alright, and we don't need to see that graph. Alright, x equals r cosine theta. Alright, and then what would y be? Well, multiply both sides by r, y would be r sine theta. And again, I don't need to see this graph. And that's how we're going to go back and forth. Oops, this should be r sine theta. And that's how we'll go back and forth from polar. Notice I have an x-coordinate, a rectangular coordinate I'm trying to solve for. It's isolated. And the other side is polar, polar. Alright, rectangular equals polar and polar. The rectangular coordinate is found by doing stuff to the polar coordinate. Over here, the polar part, if I took the square root, r would be isolated, and I'm doing stuff to the rectangular. Alright, if I did arctangent, theta equals arctangent of this, I get theta, a polar coordinate, by doing stuff to the rectangular. Now we're just reversing the process. To get the x-coordinate, we are rotating by this amount and extending this far. That's going to point to one x and one y. Alright, now let me show you. I'm going to delete all these points and stuff. Let me pause this and take away all this stuff. So this time, let's say that I have the polar coordinate 5 comma pi over 6. Okay, and this is r, this is theta. Now notice the background, the grid, all these little things are squares. This is rectangular coordinates in the background. Desmos does have a built-in polar graphing feature, and I don't use it that often, but it's there. It's this thing that's right here beside the on the grid options. So there's rectangular, this is polar. And so if you look, this is pi over 3, pi over 2, pi over 6, this is pi over 4. So this is pi over 6, and notice we're going through 1, 2, 3, 4. These are just circles of different various radii, and this is radius 5. And so we've rotated from there up to there, pi over 6, or about 30 degrees. Okay, so that's an option. You can do that if you're doing polar, but we're trying to convert from polar to rectangular. So what would this be in rectangular? Well, x equals r times the cosine of theta. So 5 times the cosine of pi over 6. What's the cosine of pi over 6? Again, look at your unit circle. The cosine of pi over 6 is the square root of 3 over 2. So r times the square root of 3 over 2. The x-coordinate is 5 times the square root of 3 divided by 2. That's our x-coordinate. R cosine of theta. Alright, cosine of pi over 6. Alright, r sine theta. What is the sine of pi over 6? The sine of pi over 6 is the y-coordinate pi over 6, which is a half. So 5 times a half is 5 halves. Alright, now, for whatever reason, it gave it the exact same color as the previous one. I'm going to change that just so you can see that if I do black, for instance. These 2 points are sitting right on top of one another. Oops. So there's our point. Alright, so 5 square root of 3 over 2, 5 halves, is the same thing as the polar coordinate 5 comma pi over 6. Alright, now this is unique. The rectangular coordinate is unique. How do I get to this point using rectangular coordinates? I go right this amount and up this amount. It's the only way that I could get there, right? But how could I get to this point using polar coordinates? Well, I can do 5, pi over 6, right? But I could do pi over 6 plus 2 pi, which would be 2 pi is the same thing as 12 pi over 6, plus 1 more would be 13 pi over 6, right? And I've gone all the way around one time, and I'm back to this point again, right? So remember, when I've gone through a point, and now the point is determined by a distance and an angle, well, I'm going to hit that point again if I increase by 2 pi. So if I zip around here and come through again, there I hit it again, right? And then I could go around again, and I could hit it again, and again, and again, right? And the same thing in the negative direction. So the polar version of that point is not unique. I could start with this distance, and I could add and subtract 2 pi from this and hit it over and over and over again. Okay, so that is not the polar version of a point is not a unique point. The rectangular is. This is the one and only representation of how to get to this point using rectangular coordinates. But as a polar coordinate, there's an infinite number because I can keep changing the angle and landing at that point again. Now, what's crazy, and we'll get into in the next video, is that there's another way to land here and keep the angle locked in. Or sorry, I shouldn't say that. No, not keep the angle locked in. Not add 2 pi to the angle. And I can land back here. Alright, and we'll look at that in the next video.